One of the higher ones we've ever had in this class. I think it was 73 was the average. Obviously, we curved that up to an 80 regardless, but you got a much smaller curve this time because it was such a high average to start with. I think it was only probably a 7 or 8 point curve. The tests themselves, one of my TAs has them, but he went home sick today before he could bring them. So we will have them on Wednesday. I apologize for the extra day delay. But here's how it looks, right? So this is your breakdown, the histogram of scores as a function of your probability of getting these different scores. So if I bend this a different way, it comes out, you can actually see like some of these clumped together. I'll post those on the announcements probably. But this was the scores. This was after curving, right? So after the 7 points right. However, I'm told that there was at least one student. Was there more than one that got 100? There was one student that got 100 even pre-curve, which is pretty awesome. The majority of students finished before time was out, so that's also a good indicator that the test was more appropriately length and difficult-wise. That was the actual scores here, and then you can see the ranked scores. Looks something like this. This was after curving because it's at an 80% average. So that's midterm 3. The solutions are up. Again, the test will be back on Wednesday. Anything else to say about that? Do you know what the standard deviation was by chance? I'll calculate that and find out for you. Okay. So let's talk about chapter 11. Okay. Chapter 11 is kinetics. Up until now, everything in this class has been, well, thermodynamics says that this should happen because the energy is lowered, right? And because it's lowered, we can see things happen. What we're going to talk about in this class today is that even though you expect something to happen, sometimes there's an additional, what we call a kinetic barrier, right? And we're going to see a great a demo with that on YouTube this year, apparently. Okay? So today's learning objectives, we're going to talk about what are these some of kinetic limitations. And to do so, we'll describe what's called homogeneous nucleation and heterogeneous nucleation. We're going to calculate the free energy as these solids start to form from a melt. So you've got pure water and you start to form solid ice. The free energy changes with the size of those particles. We're going to describe that. We're going to develop expressions for that as a function of its size. We'll calculate the rate of transformation. The rate, that's sort of the first time we're talking about that quantitatively in this class. We've sort of qualitatively hand-waving described rate, but we're going to get into ways to calculate actual rates now in this chapter. And we'll even be able to calculate how cold can something be below its freezing point and still not be frozen. Okay? So let's start out with a video on that. Okay, so maybe you've experienced this. If you've left like a water bottle in your car, you go out in the morning, you pick it up and it looks like it's water, but as soon as you grab it, all of a sudden it freezes before your very eyes. That's what this video should show us, I hope. Thank you, Lenape High School, for saving my ruined demo. Okay, so now it's better to use, the things they're saying help this work better. Fiji water works better than other water because it's distilled and it's mostly deionized. There's not as many ions in there. We'll talk about what on earth ions are and why do they mess with this demo. It also says you put it in one of these like fish coolers, like the plastic one, or the styrofoam ones. I did it in this, but it was overkill and it didn't let it get cold fast enough. What you don't want to do is take your water bottle and set it right on the bottom of your freezer, because that is far, far colder than the ambient of the freezer. And so you get really, really cold spots over here, and that's going to cause it to nucleate and grow in ice all the way through your bottle. And we're going to see that showing. Right? You cool it down to below the freezing point. They go well below it, 20 degrees, right here. They take this thing. It's now in a supercooled state. It should be ice from the phase diagram. And you take that and see this happening. It's cooler when we do it in person, but the YouTube still is a decent substitute. That's turning into ice before your very eyes, right? So, what's happening here? This chapter 11, is going to describe this phenomenon. Why does ice do that? Why didn't it form ice the second it hit 32 degrees or below that? Why didn't it just instantly turn into ice? Why is it that when you bonk this thing on the table that it did that? In fact, if you look on these, this might be one, yeah. If you pour this onto a chilled plate, watch what happens here. Liquid as it pours, definitely liquid, but it's turning into like slushy the second it hits that, and it's sort of like turning into ice before your very eyes. It's kind of liquidy ice. It's not a super solid ice, but turning into ice right before your eyes. So what is going on is what we're going to describe in this chapter. Okay. So we've described phase transformations. Let's break them. We've been talking about them, but we haven't actually broken down the different categories. So let's talk about the 3 different categories that we need to know. There is diffusion dependent, but the composition doesn't change. Okay? Diffusion dependent. That means atoms have to move for this transformation to take place, okay? But the composition doesn't have to change. There's diffusion dependent, but the composition does change, right? And then there's no diffusion, but a metastable phase is produced, okay? So think of some of the transformations we've talked about. Somebody give me a transformation that we've talked about in this class, when one phase turned into another. What do you think? Of what? Is that a metal? Okay, so yeah, ferrite turning into austenite. That's pure iron. So since it's pure iron before and it's pure iron when it ends, which one of these is it? That looks like this one. Composition's definitely not changing, right? Now, is there diffusion? That's another interesting question. Do you think there's diffusion going from alpha to beta? All right? This is a bit of a tricky one, okay? Because it might be a no diffusion one. The atoms have to rearrange themselves. So when we say diffusion, what we're really asking is the motion of atoms significant or not, right? If it is shifting from one structure to another, or is it a major shift? By the end of this chapter, we'll see an example of both of these. Another type of phase transformation might be the eutectic point, where you go from a liquid at one composition to two different solids at a very different composition. So you definitely have to have diffusion there as it changes composition, okay? Anyways, these are the different types of phase transformations we have. And in any type of phase transformation, you can have it happen in one of two ways. It can be either homogeneous or heterogeneous. Homogeneous means that if this is like your bottle of liquid, right? Homogeneous says that this is all liquid to start with, and the solid that forms sort of grows right in the middle, right? And it ends up like this large solid, okay? But it starts in the middle, right? Heterogeneous is different. Heterogeneous says you got a bottle, and there was something, a surface or an impurity, and your solid starts to grow along the side of this thing, right? So homogeneous versus heterogeneous, both of these are possible. It's possible that your ice cube forms right in the middle of the liquid and grows outward. That can happen. But it is far, far more common for heterogeneous nucleation to happen, as we're going to describe in today's class, or probably next class we'll get into heterogeneous, right? When you add a surface, something about the energy must change that makes it more favorable. By the way, that doesn't have to be on the surface of the bottle. You could have a particle, like these ions. That's why they have you use deionized water for this demo. If you take, a speck of dust, then the solid can grow around that, and it also happens at a lower energy, and therefore it's more likely to happen, okay? All right, so let's dive into homogeneous nucleation. In homogeneous nucleation, when something changes from one phase to another, it's because the energy goes down, right? Anything in this universe happens because the energy goes down. So we could say that for the reaction, alpha turning into beta, right, which looks like this. Here's our container. It started out as alpha phase. That could be a liquid or not. Let's assume it's a liquid in this case, right? If you form a particle of beta with a certain size, r, that's our beta phase, we know in order for this thing to happen from a thermodynamic standpoint that the change in energy, delta G, needs to be G of the beta phase minus G alpha better be negative. If that's not negative, then it has no reason for it to happen, right? If it is negative, we're not guaranteed that it will happen until we satisfy some conditions we're going to describe today, right? So the first thing we need to figure out is let's do this on a per volume basis. Rather than a per mole basis, let's take our moles and divide it by the molar volume. So V with the hat on it right there, that's the volume per mole. Per mole of substance, okay? So V with the hat is the molar volume. So when we take our change in free energy, divide it by the molar volume, we end up with the volumetric change in free energy, you could say, right? On a per volume basis. That's going to be important because this particle there has a volume associated with it. And that volume changes as it grows, okay? So, our first clicker question, or group question, right? So if the change in free energy of one phase relative to another is negative, why should there be any resistance, right? So if this delta G term is negative, why on earth should there be a resistance? So turn to a neighbor and discuss. Something is stopping it. You saw that the water was clearly still water, even though it should have been an ice. So what's stopping it? So turn to a neighbor and discuss. Okay, what do we think? Free energy says this should happen on a per volume basis. So what's preventing it? What's the resistance? There is an activation energy. And what's the physical mechanism? Why does that exist? Because you're right, there is an activation energy we have to overcome. What's the cause of that? The orientation of the crystals. That's a good guess. That's not right. That's a good guess. What's going on? Well, first off, if it's an energy, it has to do with either entropy or enthalpy, right? So first off, can we rule out entropy? You're going from a liquid, which is very disordered, to a solid, so it's probably not coming from entropy, right? Entropy wants to be disordered, so if you're going the other way, it must be enthalpy. Enthalpy has to do with bonds, right? Where else have we seen enthalpy and bonds cause a problem? What about if this is a region of crystal, and this is a region of crystal, and you've got this broken region in the middle where bonds aren't satisfied? This is a grain boundary. Those have an energy, but really any surface has an energy, right? We talk about surface energy because that's dangling bonds. It's bonds that aren't satisfied. This particle that's forming, that solid beta, that has a surface on it. That surface is filled with bonds that aren't in the right spot and they're not satisfied. So there's a surface energy penalty, right? So that's what's preventing this from happening. Even though free energy says it should happen, there's a surface energy that we're not accounting for. Right? So that surface energy needs to be accounted for, and when we account for that, then we can figure out exactly when it will freeze. So what this really means is at 32 degree Fahrenheit, when you expect water to freeze, or 0 Celsius, you're actually going to be able to go below that because that little bit extra below is coming from the penalty of paying that surface energy price, okay? All right, so let's go ahead and write an expression where we include surface energy, right? So our total free energy, this is our delta G, it's going to have a couple terms, two different terms. The first term has our volumetric change in free energy. So on a per volume basis, this is how much it costs to create that new phase. If that's negative, it's favorable, right? And so you obviously have to multiply that by the volume of what's being crystallized, right? Nucleated. If you assume that it's a sphere, which we're doing right now, then you just need the volume of a sphere. 4/3 pi r cubed, where r is the radius of that sphere. What we're going to call an embryo, right? It hasn't quite grown yet. It's growing, so we're going to call it an embryo, right? That's the volumetric term right here. And then we have to have another term which has surface energy included with it, right? So this gamma term, gamma is the surface energy, right? The free energy of the surface. So that better have units of joules per meter squared, or EVs per meter squared or something, right? And then you're going to multiply it by the surface area of a sphere, which you remember way back to 9th grade is 4 pi r squared, right? So there we've got it. If you account for both of these, now when this whole term is less than 0, then you should get the transformation taking place. So the problem with what we've been doing up until now in this class is we've been ignoring this term. And in many instances, you're like, it doesn't matter. Maybe it's only a few degrees. But it can be really significant. This term can make your transformation happen hundreds of degrees lower than you expected, right? In that video, they took their ice down to 10 degrees Fahrenheit. That's 22 degrees lower than you'd expect. I don't know how far you could go, but in some systems, it can be hundreds of degrees Celsius below. Okay? So, okay, we've got these two terms. Both of them depend on how big your embryo is. They've got r in it. R cubed and r squared. The question is, which one wins? If this is, say, negative, because this term is negative, and this is all positive because that's a positive energy, you have a negative term plus a positive term. Which one's going to win, the r cubed or the r squared? The r cubed will win eventually. In the short term, it does not win. We can actually see that, right? If we pull this up in Wolfram Alpha, I've plotted both of these two together. So I've got a negative x cubed plus an x squared, and this is what we get. Just going from 0 to 2, right? So from 0 all the way up till 1, it is a positive value, meaning as this thing forms that solid, we're actually going up in energy. Not a lot, but a little bit. We're going up in energy. Only after a certain size, which we're going to call the critical radii, or R star, okay? R with the little star next to it, that's this size. That means if you're above that size and you keep on growing, you start going down in energy, right? Actually, up here, excuse me, I think I said that wrong. R star is up here at the top of this, right? I'll draw this myself in a minute. At the top of this, as soon as you start getting down in energy, that's R star. Meaning it saves you energy to keep growing past a certain point. But if you're below this point, to grow actually costs you energy. Okay? So that's what these two terms look like when you plot them. We'll sketch it ourselves. We've got energy versus radii. It's going to go up, and then it'll go down eventually. So this value right here, the top of that, the maximum, that is R star. Okay? And this maximum value that has to be overcome, that was what this gentleman over here suggested as the activation energy. So that's G star. Okay? Therefore, in order to actually freeze, you have to have enough energy to get over that hump and then come back down. That's why in the video, when they take this thing, supercooled water, and they bonk it against the table, that sudden jolt of energy that they give it, all those atoms all of a sudden crash into each other, sound waves propagate through it, atoms are all of a sudden displaced in a big way. That gives you enough energy to get over the bump, and once it does get over the bump, then it keeps on growing because it keeps on going down in energy. And that's why you saw it go from the top all the way down. So had we been able to do a freeze frame camera, we could have seen the exact spot that nucleated and then just seen that grow. Okay? If there was one nucleation site. Okay? All right. So again, the key thing to take away here is that for parts of this plot, to the left of R star, if your molecules happen to sort of clump together and form a solid, if they arrange, right, they go from a total random order and then they arrange in a square or a hexagonal or whatever lattice, if they're smaller than that R star, then they're just going to redissolve again. Because it's lower energy to go back down. It'll just dissolve. And if you're to the right of that, if you're over here, then your embryo will grow. Over here, whereas here it will dissolve. Okay? Any questions so far on including surface area and the volumetric term? What if we did this again and I said instead of spheres growing, it was cubes? What would you do differently? Turn to a neighbor. Okay, what do you do if it's a cube? Let me pick on Tim. What do you think? Yeah. So instead of using R, which is a radius, that's not a helpful term with a cube. A better term would be like maybe a side length A or X, whatever you want to call it. But then the volume is easy. It's just A cubed or X cubed. The surface area you could figure out in the same sort of ways, right? So all you literally have to do is substitute those two expressions. Otherwise, it's the exact same approach, right? Okay, so the next question is, now that we understand conceptually that there should be a maximum and there should be an energy associated with that maximum, how do we actually solve for that to know what the critical radii or the activation energy is? How would you do that? Josh, what do you do? Oh, okay, so you're saying take this volume term, set it equal to that term, and solve for R. That will give you when they're equal to 0, right? What if we want to find the maximum or the minimum? What trick did we learn in calculus? That's really what you want to do. That's going to help us find the 0 and the maximum, right? So let's go ahead and do that, right? Let's take the derivative. So here I've done that. I've taken d of our free energy, dr. So I'm taking it with respect to r. So our 4/3 pi r cubed becomes r squared. The 3 gets brought here. Right? Same thing over here. The r squared, the 2 comes down. Right? We can solve. We now set that equal to 0, and that should be where the maximum occurs. So now when we solve for r, that will give us our r star. Okay? So rearranging it, this is an expression for the critical radii size. It's going to be a ratio of your surface energy to your volumetric change in free energy. Okay? And the same thing with your delta G star. If you plug in r star into this delta G expression, right? Now that we've solved for this guy right here, if we take and we plug it back in to delta G equaled 4/3 pi r cubed delta GV plus 4 pi r squared gamma. If we plug it back into there, that's how we got delta G star. Okay, any questions so far? Again, could you do this with a triangle? Could you do it with an octahedra? Could you do it with some goofy geometric shape? Yeah, it wouldn't be a big deal. Look up an expression for the volume, for the surface energy, take the derivative, set it equal to 0, and you've got that critical radii size and the critical energy that has to be overcome. Okay? The book goes a step further, and they say, well, delta GV, this change in energy per volume, it really depends on a couple things. Like, you could write it in terms of entropy and enthalpy, and they go ahead and they do so. I'm not going to sweat that you understand all of this, personally. Just realize that you can substitute this in for delta GV and do the exact same approach as before. And if you do so, you'll end up with two expressions that look like this. R star and delta G star can now be written in terms of your surface energy, the temperature at which you expected the transition. We're calling that T alpha beta. So if this is water, that would be 0 degrees Celsius, right? This is where you expected it from a thermodynamic standpoint. Delta HF, that's the change in the enthalpy for that reaction. And then you've got T alpha beta minus T. T is the temperature you're at. So this term, that's the degree of supercooling. That's how far below you are. That's how far below the temperature you are that you expected it to happen at. So for the example in this demo online, they did it at 10 degrees Fahrenheit. Maybe that's like negative 5 degrees Celsius or something. So it'd be 0 minus negative 5. So that's 5 degrees supercooled, right? They've supercooled it by 5 degrees. And I said in some systems, like metals, it can be hundreds of degrees before it solidifies, which really means that you can't trust a phase diagram. Up until now, we've been loving our phase diagrams. They've been like this magical map that guide us to the structure and properties we want. And this is telling us that you can't trust it because without knowing all these terms, you might actually have to redraw the lines on your phase diagram to account for kinetics. Okay? That's kind of a bummer. That's the world we live in. Okay? Phase diagrams are still useful, but they're not perfect. Okay? You guys don't seem as sad as I was when I learned about this. It's significantly more sad. Okay. Okay, now that we've got this expression, we can write R star and delta G star as a function of the temperature that we're at. Let's go ahead and sketch it for two different temperatures, right? So let's sketch the one that we had before. Okay, so again, here's our energy. Here's our radius. The first one we drew looked like this, where this was R star. Let's call that R star for T1. And this up here, that's our delta G star for T1. If you've got two temperatures, temperature 1 being greater than temperature 2, I want you to turn to your neighbor and sketch on a piece of paper, where should T2's curve go? How should it look different? You've got these expressions. Temperature 2 is lower still. We're still cooling down, but now we've gone even lower. How should this plot get modified? All right, what do you guys do? What's T doing? Do R star first. It's easier. If T goes even lower, let's assume positive numbers now. Don't do ice because it's going to throw you off. Assume it's like gold turning into solid gold, so big numbers. R star should get smaller. Okay. What about delta G star? Okay, what do we think should happen? We can do the two separately. First off, what should R star do? If you change your T to be even lower than T1, and let's not pick water because then you get the negative numbers that throws us off. Let's assume this is gold. Gold solidifies at some really high temperature. Maybe it's supposed to solidify at 1,000 degrees or something like that. And we're down at 900 versus 800. What should those two curves look like? Josh, what do you think?
I think that it would be steeper, so R would move to the left a little bit.
Yeah, so R should move to the left. Think about it like this. That term up there, the 1 over T alpha beta minus T, that term. T alpha beta, remember, T alpha beta is what the thermodynamics says it should happen at. So for water, that's like the 0 Celsius, the 32 Fahrenheit. So that's not changing. But the T, if we go lower and lower and lower, then that term is going to make us get smaller and smaller and smaller, right? R star is going to get smaller and smaller. Now delta G star is going to do the same thing, but it's now squared, right? So if we plot this, if we go to a lower and lower temperature, it should look maybe something like this. So this might be R star at T2, and this one over here, that's going to be delta G star at T2. Or in other words, as you keep on supercooling it below the temperature where thermodynamics says it should happen, it gets easier and easier and easier for this thing to eventually freeze. That's why you can't take water and just supercool it infinitely to some absurd temperature, because there's always some degree of vibration happening. And if you get small enough that tiny vibrations allow you to overcome that bump, it will just solidify, right? So there's a bit of a trade-off to be had in this when you do this demo. You want it to be supercooled so you get the neat demo, but you can't go too low or you'll end up with 16 frozen water bottles, which we've had in the past. Not very exciting. Okay? Any questions on this? So again, to do these sort of calculations, which you'll be doing on the homework that'll be assigned soon, today or by Wednesday, you want to be able to write these expressions for free energy as a function of R, which means you need to know the enthalpy, the temperature at which you expect it to happen, the surface energy, and then you're good to go. You can figure out these curves for yourself. Okay? Everyone good? I think we're good. Some enthusiasm. All right, let's do an example then. We're going to do this for pure gold. Okay, pure gold is supposed to melt and therefore freeze upon cooling down at 1,064 degrees Celsius. The question is going to be, let's pull it up. Okay, you find out experimentally that it can be supercooled 230 degrees Celsius below its melting point. So calculate the nucleation activation energy, assuming homogeneous nucleation, which is what we've been talking about so far. The values for the latent heat of fusion, that's the heat of this transformation going from from liquid to solid, and the surface free energy are given, and that should be joules per meter cubed and meter squared, I'm sorry about that, respectively. Okay? So go ahead and report your answer in electron volts to 1 decimal place. So again, you're solving for delta G star. We're asking for the activation energy. So try just plugging things in here. What's the... Oops. Why? Why OneNote? Why do you do this to me? Change your battery. It works so great until it doesn't, and it ruins my life. It makes me absolutely nuts. Bizarre. Bizarre. Okay, if anybody's stuck, raise your hand. We got some TAs to help if you need. I'm not getting the right answer somehow. Yeah, what am I doing wrong here? I was just wondering that. I don't think so. Maybe it needs to be in Kelvin. Let me try that. I don't think so, though. In my notes, I've got 6 EVs. I keep getting that, too. Maybe it's wrong on the sheet. That's possible. All right. I get 3.09 when I do it. Okay, answers are in. We're going to make this participation only, I think. So get an answer in, and we'll work it out together. I think it's just wrong on my sheet. It should be 3.08, I think. 3.8? Huh. All right, we'll work it out together. Okay, go ahead, get your answers in. We're going to wrap this one up. Okay, what do people think? It's going to be all over the place. There's some thought that it's between 3.3 and 3.9. Okay, some thought over here. So let's do this one together. Okay, so we're solving for delta G star. So it's going to be 16 pi. Our surface energy is 0.132 joules per meter squared. That whole term gets cubed. And then we're going to multiply this by the temperature. And I don't remember if that needs to be Celsius or Kelvin. I'm going to find out after this class and let you guys know. I think we can leave it in Celsius. I think so. Because it should just cancel out. So it shouldn't matter which terms it in because you've got temperature squared here and temperature squared here. So I don't think it matters if it's Kelvin or the other one, but I will find out for you. This does need to be squared, though. Divide that all by 3 times our latent heat of fusion, which is negative 1.16 e to the 9. That's joules per meter cubed. That thing needs to be squared. And then you're going to multiply this all by 1 over the degree of supercooling, which is 230 degrees Celsius squared. When I plug all that into my calculator, I'm getting... I see the problem. I did 0.123 instead of 3.2. Let me change that. Okay, I get 6.12 e to the negative 19 joules. Good? We're getting that? And then we can convert that to electron volts by multiplying it by this term, right? Times 6.24 e to the 18. I end up with 3.8 joules, right? Which is what a lot of the answers were. Or sorry, 3.8 electron volts, excuse me. Okay, so the only thing that I need to clarify, and I'll do so after class, is whether you can actually do that with the temperature in Celsius or if you have to put it in Kelvin. It's possible that it has to be Kelvin, so watch for an announcement after class. Yeah, question?
Kelvin, it's 6.04.
As the final answer? Yeah. And that's what I have in my notes, so I'm guessing that it does need to be in Kelvin. So watch for an announcement. I'll clarify that. I think that it probably does need to be Kelvin. Any questions on this approach, though? It's just plug and chug, watching your units mostly. Yeah?
So with the T alpha beta minus T, why don't you do 1064 minus 230?
Because that equals 230. Sorry, I see the question. You don't go from 1064 all the way down to 230. You go 230 degrees lower than 1064. Yeah. Any other questions on this? Most common mistake on this will be not watching units or just math errors. So take your time going through these, but they're pretty straightforward. Okay, let's do, and I'm pretty sure it does need to be Kelvin, but I'll clarify that after class. Let's go to our next one, which is the same question, but now calculate the critical nuclei size. And I'm pretty sure we should do this in Kelvin. Yeah, go ahead and do it in Kelvin. I'm going to change this other answer up here. The enthalpy must have, there must be a K there. Okay, get your answers in. Okay, we're going to close the poll. Okay, here goes. Okay, people think, yeah, this is the right answer range right here. About a third of the class is getting that right. So let's do this one. So you set this up just the exact same way. Now that we know that the temperatures in Kelvin was the only ambiguity, this is equal to the same exact approach as before, -2 times 0.132 joules per meter squared. Multiplied by our temperature, that's 1337 Kelvin. Divide this all by -1.1, what is it? 16E⁹ joules per meter cubed. This is all multiplied by 1 over the temperature of our transition. So that puts a 230 K down there. Why can we do 230 K as instead of Celsius there? Celsius and Kelvin are on the same scale. They're just shifted relative to each other. And since we're talking about a difference in temperature, a difference of 230 Kelvin is the same as the difference of 230 Celsius. When you plug all that in, I get 1.32 e⁻⁹. And remember, that's in meters, because that's the meters squared, meters cubed here end up with meters. So that's equal to 1.32 nanometers. Okay? Any questions? Keep going. Okay. So we now understand that there's an activation energy, okay? And the activation energy has to do with nucleation. But as something transforms from one phase to another, as you saw in the water bottle demo, it's more than just nucleation. When they sort of smacked that thing on the table and they saw it sort of start to grow from the top down, the nucleation was just part of that equation. Then you had the whole growth part of it. And they're two different processes. Nucleation and growth need to be treated separately towards the overall transformation, okay? So we're going to treat them separately. First off, we're going to deal with nucleation. So the number of stable nuclei, those are nuclei that are larger than the critical nuclei size. So if R is greater than R star, then that nuclei is stable. We're going to call that, the number of those is N star. And that's obviously a function of temperature, since temperature changes what R star is, okay? We can write it like this. It's just like we've seen before. It's another thermally activated process. The number of stable nuclei is equal to some exponent, or some pre-exponential, excuse me, times the exponential of an activation energy times your thermal energy, okay? Okay, so we could figure out what K1 was if you could somehow count the number of stable nuclei there, right? Now you remember that this term itself, delta G star, that term depends on 1 over T squared. So actually this whole term doesn't go as 1 over T. It has a T dependence, okay? Let's see. The other thing we have to consider is not just the number of stable nuclei. We have to consider the attachment frequency. So once you have something that's stable and it wants to grow, it can only grow as fast as new atoms can diffuse and touch its surface, right? So that's going to depend on diffusion, right? Therefore, if we look at this expression, the frequency attachment rate, that's going to be V sub d, that's going to be a different exponential in front of the pre-exponential, in front of the exponent. But now instead of the activation energy being the delta G star, it's going to be QD, which is our diffusion activation energy, right? So atoms that can diffuse faster will attach faster, is what that's essentially saying, okay? If we take both of those two terms together, we can now plot the attachment and the number of nuclei both as a function of temperature. So let's go ahead and do so. Make sure I do this right. Grab my note sheet. So this will be temperature. This up here, let's assume that that's our T alpha beta. That's where the phase diagram says it should happen at. We know that we're going to go below that before things start to happen. We can plot this right here is going to be our N star, meaning the lower and lower we get way below that temperature, we're supercooling it even more, we should start to get way more N star, right? So this is like the amount, the number or amount. So we're getting lots and lots and lots of our N stars at those low temperatures. But activation energy is going to do just the opposite, because there it's diffusion. We know that things diffuse faster at high temperatures. So our V sub D should look something like that. Therefore, you have this compromise, right? When it comes to transformation, it's not like, oh, just supercool it as far as you can below, and you're going to get the fastest transformation. Because if you supercool it way far below, you'll have tons of critical nuclei that can't grow because their diffusion is really, really slow at that temperature. And if you go the other way, where you're just a few degrees below this temperature, your diffusion rate will be really fast, but you're not going to have very many stable nuclei, right? So the overall fastest transformation will be somewhere in between those two. You'll see something like this. So that represents, we're going to call that N dot. That's our nucleation rate, okay? Nucleation rate. That's the number of nuclei that form per unit of volume per second, right? So we're going to take the two terms from before, N star and V sub D. So that gave us K1 and K2. You've got the two exponentials. One depends on the activation energy. One depends on the activation energy for diffusion. And then we have to have this A star term. And that accounts for the number of atoms that are at the surface of the critical nuclei. And we're just going to call that a constant. So if you take all of that together, this big nasty expression, that will give you your nucleation rate, okay? And as we said, that it doesn't happen just at high temperatures or just at low temperatures. It's a compromise between those two events. You want to have lots of nuclei, but you want atomic motion to those nuclei, so your maximum rate of nucleation is going to happen at some temperature. So this would be the fastest rate at this temperature here, right? That temperature. Call that T1 if you want, okay? That's our fastest rate. Anything other than that will be a slower rate of nucleation. Okay? Okay. We're going to talk more about what happens after nucleation with growth explicitly in a minute. Actually, we're out of time. So next class we'll pick up and we'll talk about heterogeneous nucleation.